Hello everybody, and welcome to Amii Presents Tea Time Talks. So my name is Dylan Brenneis. I'm a master's student in mechanical engineering, actually, under the umbrella of Amii. And because I'm in mechanical engineering, this talk is going to be a little bit different flavor than is typical for these Tea Time Talks, in the sense that it'll be a little bit more mechanical engineering focused. But I promise I'll make it worth your while, I'll make it interesting. And at the end, I'm hoping to have riff some ideas about how machine learning might be able to be used in a system like this. So, because really, if Amii is this big thing, and these are all the things that Amy's interested in, I would say that I'm kind of over here on the far side. All of my things are still, of course, directly related and usable in all of your other fields. But really what I'm focused on doing most of my work is building the bionic bodies that the minds that all of you folks are building will be able to inhabit and use to see the world and to be able to act in it as well. So if you remember my talk from last year, I talked about the handy hand, which was essentially an inexpensive 3D printed hand full of sensors so that the machine learning agents could really see the world. And that was kind of more on the sensation side. But what I'm working on now, my interests have moved up the arm a little bit to prosthetic wrist control. Because there's some interesting things that we can do in like how we can affect the world that way. So I'll start by talking about just your natural biological wrist function. So these are the wrists that we're born with. I consider there to be basically three main functions of your wrist. The first one being to keep your hand fixed relative to your forearm. So if you're, say, holding onto a hammer, you want to swing that hammer and keep it fairly straight so that you know what you're doing with it. So that's the first function of the wrist. The second function is to kind of reorient your hand relative to your forearm. So this would be, for example, like turning a doorknob, where your forearm kind of stays pretty much the same, but you can change the orientation of your hand. The third function, which I consider to be possibly the most interesting, is essentially to keep the hand fixed relative to the ground plane, or gravity, while you're moving the rest of your arm around. So we would do that naturally, say, in picking up a cup, so that we don't spill what's inside it. So you see, like, the wrist motion here it's a complicated combination of many things to keep this wrist level, the hand level, the cup. And if you were an amputee person using a prosthetic arm, basically your wrist really wouldn't have these three functions. Typically, you can group prostheses into two main categories if they have wrist function at all, and that would be whether that wrist function is passive or active. So a passive wrist would be one that you have to go in with your intact hand, if you're lucky enough to have one, and actually change the rotation of your wrist or the flexion of your hand, then go ahead and do your task. And if you have to change in the middle, well, you have to stop, reorient, and then continue. So that's a passive wrist. If you're lucky enough to have a myoelectrically controlled prosthesis, so electrically controlled using your old muscle signals, your active wrist can be controlled using those same signals. But in all commercial systems, you will have 1 degree of freedom instead of the 3 that is normally in the wrist. You'll either have flexion extension or rotation, never both. So when you buy the thing, you have to choose which one you want. And you can also only control one joint at a time. So if you're controlling your elbow, then your wrist is locked in place, and so is your hand. If you want to control your hand, then your wrist and your elbow are locked. And you switch through a list, what's known as sequential switching, to which joint you're actually controlling at that point in time. And the reason that they're like this really is because if we were to be putting all the extra, the whole 3 degrees of freedom in a prosthetic wrist, it becomes very bulky, very heavy, and that extra weight is not really worth carrying around if we don't have a good way to control it anyway. If you're just adding those 3 degrees of freedom to an even longer list to cycle through, then what you end up with is people basically just compensating using their natural arm instead of their prosthesis. So what most people will do, whether they have a fixed wrist or an active one, will use their body to compensate and pick up. And if I wanted to keep this cup level, you notice how I have to use like all this shoulder and elbow motion and like crouching down and that sort of thing. And the reason this is because commercial systems only allow those first 2 functions of the wrist, the fixed wrist or direct control of the actual wrist itself. So my proposition then is, what if we put in that third function? So I just gotta find my mouse here. This is what it looks like if we put in that third function. So you can see already that if I'm trying to pick up this cup, I can go over here fairly naturally without any weird compensations, and I can go quite a bit higher and lower than I would have been able to with a fixed wrist. So that's the kind of control scheme that I'm proposing that we start to implement. So basically how it works is I have an IMU stuffed into the base of this hand here, and that's like the coordinate system of that IMU. And it can see where gravity is, basically. So it'll always feed back this gravity vector, and this is always pointing straight down into the earth, no matter what the orientation of the IMU is. And by looking at the projections of this vector on the XY and the ZY planes, I can find the pitch and the roll angles of the prosthesis at any point in time. So basically what my controller is doing is using what's called a PID control to basically keep the angles to whatever they were when you entered the auto leveling function. So if you're, let's see, if my wrist was here when I went into it, then it'll keep that level. Or if it's more level when I start, then it'll keep that. So it basically just keeps the same as it was whenever you entered into the thing. Yeah. But of course, automatically leveling is not always a good thing. For example, if I have this cup and I want to pour it out, it's a little bit tricky. So we have to think of this leveling system as just one part of more of a complete whole. And so we need a way to switch in and out of the auto leveling system. So, but there's a lot of different ways we could do that, right? We could what I have right now is a button that's just like toggling in and out, but we could do a held button press. So like if it was always auto leveling, unless you were holding the button down, then it would be ready to pour, or something like that. Or we could have an entirely separate alternative control channel that we could jump in and say, okay, now you're directly controlling the wrist angle, for example. And then underneath all of those is like, okay, well, what should be our default function? Are we auto leveling all the time except for when we want to tell it not to? Or are we fixed all the time except for when we want to tell it to auto level? So these are a lot of different ways to control, and you can imagine that this is going to have a great impact on how easy the thing is going to be to use. And so that's going to compound any kind of, like if we're trying to see how the compensatory movements change when someone's using this, if we can't tease that out from whether the thing's easy or hard to control, then it's not a great experiment. So we had to do a design study first. And what we did basically was we had 6 different ways of switching in and out of the auto leveling system. Modes A through E are all involving this auto leveling, this third function. And the control condition was your typical sequential switching. So you're switching between fixed control and direct control of the wrist. And so basically we were comparing first whether the auto leveling helps at all, whether it's worth looking forward to in the future, and then secondary being which modes or which features of which mode would necessarily be the easiest or the hardest. So each of those 5 modes is basically made up of those things from the other slide, whether you're momentary toggling between, whether you're holding a button, or whether you have a secondary input, and then just switching out what's default and what's not. So the experiment that we ran was with 6 able-bodied people using a desktop-mounted robot arm. So not on the arm as you see here, but like fixed to a desktop and not actually attached to the person. And only 1 degree of freedom at the wrist. So that was the flexion extension, this guy here. And it was mapped to the elbow position so that whenever the elbow moved down, the wrist would move up, so that it would just keep level in that plane. So there was 2 tasks. First you had to take a cup from a low spot to a high spot, which required some kind of leveling scheme, whether manual or auto leveling, to avoid spilling beads, because the cup was completely filled with beads. And then the second task was to pour the beads into the sink. So that would require the person to switch into and out of the auto leveling. Yeah, and we just did 10 trials of each over and over again, and this is kind of what we came up with. So what we can gather from this, the yellow is the control condition, the typical sequential switching. And all of the lettered ones have some kind of auto leveling. So you can see that especially in these these measures, the number of spills per trial and the average number of like control switches, the auto leveling outperformed the control condition pretty well all across the board. So that was a good motivation to say that auto leveling is something that we should continue looking into. And then within those modes, we were able to kind of see that the momentary button press, toggling in and out, performed better in terms of like spills and switches as well, better than the held button press. But the alternate control channel, having a separate joystick on the Xbox controller they were using, performed the best across all categories. We also had a qualitative survey just to kind of see how people liked to use the thing, whether it felt like it was easy to learn and that sort of thing. And what we gathered from this basically is that everybody's favorite was pretty much the alternate control channel, the separate joystick. They felt that it was the easiest to use and it was their preference. But notice that it's not actually significantly different from A and B, which were the toggling, the momentary button presses. And basically the held button presses, everybody hated them. They were awful. So that's what we learned from that. So moving forward, we wanted to move to a 2-degree of freedom wrist, which is what we have here. So I have rotation and flexion on this particular wrist. And we wanted to be able to use EMG control. So like an actual amputee would be using their muscle signals. And in an EMG system, having a separate control input like everybody enjoyed having on the joystick is not exactly feasible because you only have so many muscle sites to work with, especially on an amputee, right? So that kind of ruled out that particular control scheme. And so what we ended up going forward with was the momentary switch, which was by far the second best. And it switches between direct control and auto leveling. So whenever I'm controlling the wrist, it levels in terms of rotation, but I can still move the flexion. And then whenever I'm in hand control, opening and closing here, that's when it's auto leveling both rotation and flexion. So basically what we've got now is this system as you see it here. The power all comes through here on my hip with a fancy light that you can turn on and off if safety is a concern. And all of the control signals are coming through on this bicep hub. And of course the prosthesis is mounted on my arm. It's restricting my natural wrist motion so that I'm essentially, it's a prosthesis simulator, right? So I can't use my own wrist. I have to depend on the wrist of this actual system. And the idea of putting it on able-bodied people first is that we can run through a lot of people very quickly without having to go through our amputee population, which is necessarily smaller. So the study that we're going towards is using motion capture. So we have a space in our lab that has 8 different cameras set up that all point towards a person and track different markers that we're placing on the arm. And we can actually quantitatively analyze how these compensatory movements are going to change. And also we're tracking the eye gaze, so I can see kind of what you're looking at. And if you're focusing more on the hand with one particular control mode than the other, I can say that that one probably requires more cognitive load to operate. So I'll be comparing my auto leveling system to the regular sequential switch, and then also a standard fixed wrist control system. And if anybody's interested in being a robot arm jockey for a while, I'm recruiting participants, so please let me know if you're interested. But perhaps more interesting for this particular crowd, how machine learning could be involved in a system like this. There's a lot of ways that I could think of, and I'd be happy to hear your thoughts as well in the question period. But first off, like, when to switch? When is appropriate to use an auto leveling scheme versus a fixed wrist versus direct control? And if the arm has enough sensors on it to kind of see where it is in the space, what it's doing, it could perhaps make a prediction about what you want out of it, what kind of control scheme you're really looking for. So that would be an interesting thing to look at, certainly. Second being either just tuning of the PID control or just direct replacement of it. You'll notice, like, there's a certain amount of lagginess and overshooting and oscillations when I'm moving quickly. And that's going to be inherent in any kind of improperly tuned PID control. And the other thing with PID control is you have to tune it for particular conditions. If I'm holding something heavy in here, it's going to need a different set of parameters slightly than if I'm not holding anything at all. And so to tune it for every possible case is like a crazy problem, and something that perhaps machine learning could look at. Or if we have 3 degrees of freedom at the wrist instead of 2, that massively explodes the state space of things that we can be in, and all of a sudden I'd have to rework all kinds of classical robotic control to figure out how to even do it. So perhaps a machine learner could just like, where's gravity? Keep it the same, you know? That might be fun. Another thing being alternative leveling planes. Gravity might not be the best way all the time to level to. What if we have a slanted surface that I want to set something down on over here, but I can't because it always keeps rotating the other way? So we could look at doing something like that, having the machine learner kind of guess what you want to level to, and go ahead and do that. So that's pretty much all I have for now. If there's any questions, I'd be happy to take them. Thank you. Yeah.
I have a pretty dumb question.
Sure.
How do the amputee control this thing, like the buttons and stuff?
So if we were using an actual amputee participant, we wouldn't be using this joystick control. It's what I'm using today because it's a lot easier. But I have this little guy here. It's called the Myo armband, and basically what it has is little electrodes on the inside. So you could slide something like that on the residual limb, or there are more robust clinical systems that have place-on electrodes. But basically what it does is whenever you're flexing your muscles, whatever residual muscles are left, they put out an electrical signal. And we can read that almost like a joystick. It has some proportionality to it, or you can use it as like a button switch, on-off. Yeah.
So to follow up on that, how many input signals would you be trying to get out of that?
To run a system like this,
Yeah.
I would need 2. So you'd have like your biceps, your triceps as the antagonistic muscles, and then co-contraction, putting them both together, would be like your signal to switch. But you could use a pattern recognition system to get more function if you were looking at more than just like the wrist or hand control. Sure.
You'd have one mode that involved both wrist control and hand open close, right?
So whenever I'm controlling the hand, the wrist is controlling itself. That's the auto leveling scheme kind of taking care of it. So I'm not actually inputting anything in terms of a signal to control the wrist at that point. Yes?
Have you looked at or thought about how if someone sort of a fixed wrist here, restricting, so that'd be like emulating like a transradial amputation?
Yes, yeah.
Versus like a transhumeral amputation where it's a lot higher, they don't actually have the elbow or the same rotational ability, how that would actually affect the efficacy of the control system you're looking at, and then also just like how difficult they find it to use, and then if they actually perform better with it.
That would certainly be interesting to look at, because like what I'm using an awful lot of elbow motions here, which if I was a transhumeral amputee, I would be having to use my prosthetic elbow, or more likely I'd be using shoulder abductions. So to have an auto leveling wrist, I mean, it would still level in those situations. Whether I'm going out with the shoulder or up with the elbow, it's still going to level. I wonder if it would be more helpful for transhumeral amputees because there's so many more things to control as a transhumeral. Then that's just one less thing to worry about. I'd be curious to try that out, perhaps with an adaptable socket. Would be good. Yeah.
With the accelerometer, can you actually, like, does it get confused when you accelerate your hand? Like, does it know which way is down versus, like, your arm? Like, is it pointing down in terms of acceleration, or is it actually gravity?
It's actually gravity. So the IMU, the one that I have here, puts out magnetometer values, accelerometer, and gravity. So what I believe it's doing is scrubbing the accelerations away from the actual gravity vector. So if I like shake this sort of thing, it can still kind of sense where gravity is, as opposed to just the actual accelerations. It's not perfect, of course, but it works pretty well.
And sometimes you might actually want to track acceleration, right? So if you've got like in a cup, then you actually
Yeah. Yeah, so if I was turning around a corner in a car, I would want it to go, yeah. Which, I could put that in there. I could. That's a neat idea. I like that. Yeah.
Sorry, dumb question. You said, what is the thing on your waist?
On here?
Yeah.
This is basically where the power is coming in from the wall. It's all routing through here before it goes up to this, where it actually starts to control the servos. So this is just basically, after it comes through this adapter, the DC power on this wall. So, and then it's a power switch as well. Yeah. Yes.
Okay, this is kind of a weird question. Sorry about that.
Sure.
It's more biological, but you do, as long as your motor cortex is functioning, you do have signals coming out of there.
Mhm.
And, you know, it may be invasive to try to get them, and it's not always easy to read them, but I'm just wondering if that's a way to control as well, because you're telling your arm to do something, but your arm either it is not listening because you had a nerve severed somewhere, or it's just a missing arm. So
Yep.
is there a way to do that? That may not be what you like.
Yeah.
That's
Yeah, that is outside the scope of what we do in the lab, because we're trying to keep outside of invasive technologies, but there are definitely people looking exactly at that. Whether it's looking at, for example, EEG, skull caps, that sort of thing, or more invasive technologies there, like Utah electrodes, slanted arrays, and that sort of thing. But from my understanding at this point, the signals that they're getting out are still fairly muddy and noisy and things like that. Which, I mean, machine learning could do an interesting job of figuring out what the patterns are there as well. So there's just kind of two ways of approaching a similar problem. We'll see which is best. Yeah. Yeah.
So at the end, you kind of mentioned the PID is difficult to work with for some reasons. Like if you have a different cup or something, it might be too heavy. Is there a physical way around that by using different hardware, or do you have to because you mentioned machine learning might be able to solve it, but you have to use machine learning?
So the way PID works is it basically looks at the response of your system. And so whenever you're changing your hardware, your system's going to have a different response. So you can kind of think of it as like a soft spring versus a really hard to pull spring. They're going to have different responses in terms of how far they go twang, you know? So different hardware would certainly give a different response, but what you're doing with the PID is tuning it to that particular system. And because the introduction of outside things like a cup to your system naturally changes the way that the things are going to move, like the natural oscillations and that sort of thing, you wouldn't be able to. So if you wanted to tune it for everything in that range, everything that it could pick up, you would have to test with a wide range of weights and tune your PID parameters specifically to each of those weights. And then have a sensor so that when it was holding something of that weight, it would use those particular parameters. I mean, which could be done, but I'm not sure it would be worth it. Yeah.
Are there any alternatives to a PID at all?
Probably. Yeah. I'm getting a lot of the engineers over here nodding. So there most certainly is. Something that I should look into before my defense. Yeah.
The signals that come to your arm when you're trying to do a complicated motion, is each of those one signal, or is it like a series of signals that does a complicated motion?
You're talking from your brain? Like through your actual nerves?
Yeah.
Sorry?
The thing that you read in your bicep or tricep,
Ah.
you said you read something?
Yes, so those are actual muscle signals. So they're not necessarily the signals necessarily coming from your brain. The ones coming from your brain tell your muscle to contract.
Yeah.
And then the contraction itself actually generates an electrical impulse.
But how do you differentiate between the impulse for like this or like this?
Because different muscles, for example. So my bicep tells my arm to move upward, my tricep tells it to move down. And so that would be the two signals that I'm reading, is the up and the down. And that's how I would differentiate there. Yeah. because the two muscles are on different locations that I'm reading. Yeah. Yes.
This is maybe more on the cognitive side of things, but when humans want to do something like this, right? So I'm trying to imagine if you're holding a cup, you have sort of a subconscious way of, sort of leveling it. But if you're trying to push something with your forearm, so your focus is not on your hand, then you just kind of turn off the leveling machinery for your end effector, right? So I was wondering, like, do we have any ideas about how much human, like, able-bodied humans, like, what kind of cognitive resources they have for something like this? Or do we also have like a mode switching system? And how good are people at this task? Like, could this sort of thing be useful for able-bodied humans in some context?
I don't know if there's any research on that in terms of like how often we think about the way that our arms are moving. I don't know. That's something interesting to look into, certainly.
Iron Man.
Yeah.
Or like a tea carrying machine, so if you've got like an extra
Yeah.
that carries your tea for you, as
Yeah.
you go around.
Or if you're dancing at a party, don't want to spill your drink.
Yeah.
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 Yeah. Cool. Well, thank you all very much. It's great.